Hello, George. How's it
I'm,
going?
I'm all right. How are you?
Doing well, thank you. I see you've got the guys behind you again.
Yeah, they're still here, man. They're still waiting. They're waiting on me.
They're
They're
waiting
waiting
very
on me.
patiently.
We really should make a video just to figure out who all these people are.
That would be really
Uh,
cool.
yeah,
Let's do
it
that next
would.
time.
I mean, next time, yeah, we have more important things to talk about. All right. So I think, what do you think we should talk about today? What do you got in your background over there?
Well, what is attempting to be the Poisson distribution probability mass function, but you can't really see it very well. I need to work on these backgrounds.
No, that's okay. That's okay. You show a little bit, like a little bit of a puzzle, and then we fill in the puzzle as we move along. Is Poisson, right? Is that how we pronounce it?
That's how I pronounce it.
Well,
How would you do?
Poisson. If any way I pronounce it, it's probably incorrect. So I'll go with
It's French.
I'll go with yeah. So me being from the States, sometimes I asked one time I went and I asked for a hot chocolate, and they're like, "Excuse me, what?" And then I'm like, "A hot chocolate," and they're like, "Oh, a hot chocolate." I'm like, "Yeah, that's what I meant." But so I can kind of butcher it a little bit, but what's not? So I think is it like I think that distribution kind of talks about like accounts, right?
Yeah, I would say so. It's a discrete probability distribution, isn't it? And it is, well, it describes count data. It's the probability of an event happening within a certain space and time.
Yeah, that's right, exactly. So we have a specific, let's say a unit of some kind of a time, let's say a time interval, let's say a day, right?
Sure.
And there's a certain event that might happen per that day, and there's an average amount of time that particular event might happen. Are we able to predict the probability of some other amount of that particular event happening another amount of time, a different amount of times? So let me rephrase that. So as an example, I always use this. All right. So I sell pizzas, and usually about 20 pizzas a day is what I average. I
Pretty
might
good.
ask myself the question, well, what's the probability I'll sell 40 pizzas today, right? In that same interval of time. Okay,
Sure.
so pizzas per day, or if we're talking about some other counts, maybe not per unit time, but maybe per unit area, like how many flowers pop up in a square meter or something like that, on average. And you may ask yourself the question, well, what's the chances of this many flowers popping up over this square meter? Okay.
Oh.
And I think what we have to assume is that any period of time, let's say any day is no different than any other day.
That's right.
Right. And I'm not sure exactly what the other conditions are, but there's some conditions there. Okay. All right. So let's see if we can figure out what the rest of that equation is, and then kind of look at some of these, how to use it, basically, maybe using Excel as well, right? I think we've used Excel before, and it turned out okay. But the birthday problem, I think we did, right?
I'd say so.
All right. So we have the probability, right, of our random variable x equaling some value. This would represent, in our particular example, if I tell you that the average amount of pizzas I sell in a day is 20, I may ask the question, what's the probability I'm going to sell 40 pizzas? Okay. So my lowercase x represents the actual value of how many times this event is going to happen that I'm trying to find the probability for. So in this case, lowercase x would be 40 in this case. And this is, there's an E involved, there's a lambda, there's a exclamation mark, probably for a factorial. Is this down here? I'm not sure. I hope you have a reference there. Does it start to look?
I do. Yes.
I think
So we've got
I think there's a negative here, maybe lambda,
That's right.
and maybe a lambda to the x.
Yeah,
Is that it?
you got it.
Wow, all right. Pat myself on the back for that one, huh? Yeah, it looks kind of complicated, doesn't it?
Maybe a little bit, but we've only got two sort of things we need to pay attention to, the lambda and the x, and we already know those.
Yeah, that's true. That's true. Maybe like the derivation of it, that might be a little bit more complicated. Should we tackle that in a different video?
I'd have to prepare for that one, I think.
The line is, of course, I already know, but we don't have enough time here.
Of course, yes. We'll edit that bit out.
For that bit, right? I think Fermat was the same thing, didn't he? Saying, it's a little bit too complicated for these margins here, and then, we have to solve Fermat's prove Fermat's last theorem about 350 years after that all happened. So,
of course.
So we'll tackle that on a different day, right?
Yes, when you haven't got the guys behind you. I might embarrass myself.
They're waiting and it's cold and it's a gloomy day and wherever we are right now.
Absolutely.
So basically we can ask the question. So when we ask, what values can x take on, lowercase x, I guess the lowest amount of times something can happen per day or per square meter would be what?
0.
0, right? So we start with 0, could happen once, twice, and you can see that this is can be infinitely long. Not very probable that I'm going to sell 1 billion pizzas if I'm usually selling just 20, but there's a probability that we can be able to figure out even for that situation.
Oh.
All right, cool. So right on. So if I said in our particular case, I'd be asking, so do you want to make any predictions? Is it really, really, really what would the probability be of selling 40 pizzas when I'm usually just selling 20 pizzas per day? You think it's like maybe 1% or 10%?
Good question.
What do you think?
It's certainly going to be on the lower end of the scale, isn't it?
Yeah, I imagine it's going to be low. Take a stab at it?
Sorry, say again?
I said, do you want to take a stab at it?
Oh gosh, I don't know.
I'm gonna make a stab. I'm gonna take a stab at it too. I'm gonna say 0.00. I'm gonna pick 3.
Oh goodness me.
That's what I'm gonna say. That's what my instincts are telling me. How about you?
Well, I was gonna say 1%, but I'm not sure
1%.
anymore.
Hey, come on. That might be the case. 1% chance. It might be. So let's see what we get. Okay. So we're actually asking then, what's the probability that a random variable x, how many times this event's going to happen per unit that we mentioned, right? In this case, how many pizzas am I going to sell in a day? What's the probability that the pizzas I sell in a particular day is 40? That means that we take e raised to the negative 20, I believe, right? And that would be 20 to the 40. Ooh, that looks pretty big. Actually, it's a pretty big number there. Divided by 40 factorial, which is also a big number.
Yes.
Okay. Do we want to try to see what that is? Can you punch that into a calculator or something? Or
I don't have a calculator on me, if I'm honest.
Oh, a mathematician with no calculator? That's
I know.
That's all right. We know what we do have. We have Excel, don't we?
Fantastic.
That's what we have. I can tell. You're ready to see this. In fact, why don't we just set up a whole distribution? And
sure.
We can even draw a little graph to see what that looks like over, from 0 going on to infinity for 1 billion pizzas, right?
And we can see where our predictions coincide with. What numbers? What value of x?
What's the bet gonna be? Whoever's closest is gonna do what? Buy lunch or?
I don't know.
Oh, man.
We're on opposite sides of not even in the same country.
That's true. How are we gonna do that? That's okay. There's delivery, isn't there?
That is true.
I'm just kidding. I'll be honest with you. Let me share this so you can see what's going on. I made it pretty big, hopefully. Is that too big?
That's fine.
Is that okay? All right,
Thank you.
All right, so let's, sure. So let's actually now put in our X value. Or actually, let's say lambda. Lambda, or mean, let's say mean instead. So lambda represented the mean, we said 20, right? And then our values for X started at 0 to 1, and then on to, we said 40. Let's try all the way up to 40. Boom. Okay. So we could actually, should we check and see if our equation works, and then actually use the Poisson distribution, the Poisson function within Excel?
Sure.
All right, let's do
Let's
that,
do it.
right? Let's do that. So let's say probability of our X equaling our lowercase x, right? And a standard notation here. We said equals to, what was it? The exponential?
Yep.
So exp, I believe. And I need to click this guy, right? And raise the exponential to be -1 times our mean, I believe, right?
Yes.
Okay.
And this is where we need, sorry.
Go ahead. No, go ahead, please, go ahead.
I was just going to say, this is where we need our dollar signs
That's
to make sure it
exactly
stays.
right. To make sure that when we copy it down, it's always using 20 as the mean.
Yes.
Fabulous, fabulous, fabulous. That's F4, right? F4, I think we get for that. I don't know if it's different on different, if it's different on Dell to whatever, the Apple, all the different kinds, but we could also go in and put those dollar signs in manually, but F4, I believe, works. So EXP raised to the -1 times our mean, our lambda, we'll close that. Now we need to, what was it? Multiply by.
It was lambda to the power of small x.
All right, so lambda again, F4 to keep that as a absolute reference. And that's raised again, right?
Yes.
Up caret to the actual X value. That's going to be a relative reference, so we can copy it down, right? Okay. And now a division, right?
Yes.
Division by, let's say, factorial. Fact, I believe it's factorial. Our number was what? X, correct? So that's that guy, and that's going to have to change. Close that, fingers crossed. Probably a pretty low number. Yeah, times 10 to the -9 here. So what's the chance I sell no pizzas? Very slim. Very slim. Again, if we could take one day to be exactly the same chances as the other day. Okay, so if something happens, catastrophic, you don't sell any pizzas, doesn't mean that, there was 1 in a billion chance, probably something else at play here, but. All right, so let's see. Let's make another bet. Okay, no non-money, no money. We're not advocates of gambling.
Of course.
But what number would you imagine has the biggest probability?
Well, I probably would have said 20.
Yeah, that's right, 20. Now, what am I to pick now? Because you picked the best one. What am I to pick as my guess if we're going to have a bet? Because I wanted to pick 20. I'll tell you what. I'll pick 19.
Sure.
Okay. Who's going to win this bet? I think you're going to win this bet. 20 and 19. Let's see. Oh, look at that.
Gosh.
What happened there? We both got exactly the same probabilities.
Look at that.
How about that, eh? Was that intuition that told me that? Or did I know something?
I don't know. Did you know something?
I noticed, I've run this before, and I always noticed, I'm like, wait a minute. I'm like, okay, obviously, the mean is going to have the biggest probability. It seems safe to say that. Sorry, I'm getting it. But I always noticed that the number right before the mean also had that same probability.
Nice.
And it becomes, it's an issue, it's basically where we get something to cancel from the top and bottom. And the probability for 19 happens to be exactly the probability for 20. So
Ooh.
I invite our viewers to kind of see that and see why that specifically happens. Doesn't happen though, if the mean isn't an integer.
Ah.
So if, let's say 20.1 was our mean, now I think that you'd be winning. Yeah, you'd win that bet. Yeah, so good thing. That was 20. So it's a tie. Nobody has to buy anybody else lunch, okay?
That's fine.
All right, that's okay. You're okay with that, right? Okay, let's see what 40 is. I think it's even less than what I thought. Yeah, man, it's a lot less than what I thought.
Goodness.
So we got 0.000003. What did I say?
You put 0.003, was it?
Oh man, no, something, don't I win something just for like not including the zero in there? Right? I think that's what I said. It was, let me check this out. Let's see. It was, what was it? Yeah, that's what I picked, but it was 0.00003, right?
It was close.
It was close, man. Just 2 zeros off, I guess, huh? Or 2 orders of magnitude off. All right. Yeah, so let's see what that actually looks like now as a graph and see how it might change. All right. So let's say we'll pick these two again. And we'll set up a scatter plot. Oh, sorry, I'm not sharing the appropriate thing, am I?
I was going to say, I can still see the whiteboard.
I'm sorry. Let me put the Excel sheet up here. Okay, so we see that. Okay, so let me highlight these bits here. All right. So the X's as well as the probability associated with those X's. And let's go to insert. Insert. Charts. I'm going to go with that.
Very nice.
Almost looks kind of normal, doesn't it?
It does. I was just thinking, having just a brief look at those probabilities that came up on the sheet, I was thinking it's probably going to be comparable to the normal distribution.
Yeah, because of that symmetry that's involved. What do they just do there? There we go. So if we change this now and make it, I think it happens to look somewhat normal when the mean is kind of big. Let's see if we change this to, I don't know, let's say 1. That doesn't look that looks a lot less normal, doesn't it?
That's very different.
I'm sure there's probably under some conditions you might be able to use the normal distribution to be able to estimate the Poisson, possibly.
Cool.
All right, so how's that?
Very nice.
Yeah, we got nothing else to say about the Poisson distribution?
Not that I can think of.
All right, it's relatively simple. Like you said, there was a couple of parameters that we needed. Well, we needed a parameter, we needed to know what the mean was. Excuse me. We also needed to know what value of X we were interested in. But we easily set up that whole distribution. So all right. Cool.
I presume that the Poisson distribution wouldn't work then if the values aren't independent.
Right. Yeah. If there's something, if one of the conditions for us to be able to use Poisson is that in our particular case, that any one day, the probabilities don't change. There's nothing. It's basically you're getting the same. Each one is independent of each other, and so it might not work in every situation. Like when there may be like seasonality. Like you can't say 1 month is the same as another month, possibly because of some kind of things that are going on in the background, or maybe even from year to year, I guess. But depending, I guess, people that are actually doing the analysis will be able to kind of, know when there might be something else at play that's not allowing them the same probabilities on 2 different days, because maybe those days are special days, I guess.
Exactly.
Right? But pretty useful, isn't it? Especially when you deal
Indeed.
with count data.
Sure.
All right, that's the Poisson video.
There we go.
And maybe next time we'll talk about, I don't know, should we give a little hint what's gonna happen next, or just
We
keep
leave
them,
it on a cliffhanger.
keep them waiting, I keep them, how do you call it? Yeah, hanging on the cliff, right? Just wait to see what's gonna happen next.
Cool.
All right, Laura, I'll talk to you soon, okay? Thank you so much.
Thank you.
All right,
I'll see you next time.
I'll see you next time. Bye.
Cool.